Everybody, welcome to this very special event. My name is Angel Abbud-Madrid. I'm the director of the Center for Space Resources here at the Colorado School of Mines. This is a research center that for more than 20 years has been focusing on how to develop studies and technologies on how to identify, how to collect, how to extract and utilize resources beyond Earth. But before we get started, I think it would be important to say, what exactly is this resource that we're talking about? How did it end up in space? And how are we going to utilize this and why? Go back to the night of October 3rd of 1957. That night, okay, if you have, after hard days of work, you would go out in your backyard, you would have looked at the night sky, beautiful sky, and you would have seen a lot of twinkling stars. The moon was pretty close to where it is right now, about 80% full. You would have seen Venus and Saturn shining brightly there. And you would just enjoy this beautiful, unadulterated, clean, natural night. That was about to change radically and forever in October 4th of 1957, when the Soviet Union launched a spherical metal piece, the first human-made object that went into space, and that ushered us into what is now the space age. That was Sputnik. Dozens and then hundreds of satellites and objects were sent by the Soviet Union, by the Americans, then by all sorts of different countries. First to send these objects to test rockets, to send things into space. Then they realized these satellites could be good for weather forecasting. Then they started sending more things for probably communications. Started moving away from low Earth orbit to mid-Earth orbit, where now you have all sorts of satellites for global positioning systems. Then into geosynchronous orbit, more than 20,000 miles away, where most of the communication satellites are there. Then you started sending all sorts of probes to the moon, to Mars, and everywhere in the solar system, to the point that this is how the night sky looks now in 2021. Yes, many of these dots are perfectly working satellites that are helping us with all sorts of things here on Earth, but thousands upon thousands of parts here are literally trash. There's what they call space debris. Space debris that countries and companies alike now all agree that needs to be cleaned up, so that not only we can enjoy a better night view, but also that can help us prevent any accidents with all the infrastructure that we have in space nowadays. But wouldn't it be great if we could not just clean up these elements and send them down to Earth and burn them in the atmosphere, that we can actually use this type of things, that we can collect this material, that we can extract some important elements, that we can utilize. That is exactly the reason for this event, in which we're looking at trash to treasure. And this is an event in which we're going to have companies represented here: Astroscale, Nanoracks, CisLunar Industries, and Neumann Space, to talk to us about their plans for developing technologies so that we can see how they're forming what we call the space debris value chain, how they're injecting themselves in all of the important links of this chain.
Hello, good afternoon, everybody, and welcome to Adelaide, Australia. Before we start, we would like to acknowledge that we are meeting here today on the traditional country of the Kaurna people and pay our respect to elders past and present. It's now my pleasure to introduce the US Consul General from Melbourne. So Ms. Lively is a career diplomat born in Washington, DC. She has over 30 years experience serving the US government in US and overseas, which has taken her to many countries, including Kenya, Romania, UK, Japan, Poland, and Afghanistan, before recently moving to Australia. Thank you for being here. We really appreciate that. The floor is yours.
Thanks very much. I would like to thank Neumann Space for the invitation to speak with you today. And I want to acknowledge that I'm speaking today from the lands of the Bunurong people. And I want to pay my respects to their elders, past and present, and Aboriginal elders of other communities who may be joining us today. I also want to acknowledge the other participants around the world: the Colorado School of Mines, CisLunar Industries, Nanoracks, and Astroscale. The technologies you're developing together are really simply incredible. Australia and the United States share a long history of working together on space. As many of you know, Australia was instrumental in the Apollo missions, a legacy that continues today. But when people talk about the US-Australia relationship, often the focus is on defense, particularly in South Australia. And while that part of the relationship is really important and will certainly continue to grow, it's collaborations like these on civil space technology, quantum, cyber, artificial intelligence, all growing industries in South Australia. These will take our friendship, our partnership, and our alliance into the future. These and other emerging technology fields can inspire a new generation to work together and develop technologies to quite literally change the world. And after the recent Quad Summit in Washington with President Biden, Prime Ministers Morrison, Modi, and Suga, there was plenty of commentary about the various outcomes of the meeting. But one announcement went a little bit under the radar, and it was an agreement to create 100 Quad STEM fellowships, where 25 exceptional students from each Quad country, the US, Australia, India, and Japan, will be given a scholarship to study STEM at elite US universities. Quoting President Biden, these fellowships will build ties among the next generation of scientists, researchers, and technologists, all coming together to take on a key challenge of our age. The folks here today are clearly one step ahead and are already building those ties, all by themselves. The Australian space industry is growing in leaps and bounds, and I am really proud. It's a story of true, trusted partners. The possibilities are incredible. We chose to go to the moon all those years ago, as according to President Kennedy, that goal would serve to organize and measure the best of our energies and skills, because that challenge is one that we were willing and able to accept. And the term moonshot has even become a popular word to describe goals that have a high bar, but inspire us to achieve great things. Now, we ambitiously seek to go further in space than we have gone before. And it would be impossible to do so without thinking about the scarcity of resources and sustainability in space. The technologies on show today demonstrate that even with finite resources comes incredible innovation. And I applaud the companies here for thinking bigger, about using what's there, not just relying on digging up more resources, but instead using something old to make something new. This is the mindset that will get us together from the moon to Mars. The people here today represent the next generation of the Alliance, organizing the best of our energies and skills. They are addressing a key challenge of Artemis. How do we work together to support sustainable deep space exploration? I challenge anyone to think about the real possibilities of recycling space junk into rocket fuel and not come away with a smile and a spark of hope that this could be the start of something big. And certainly when I was researching the companies that are here and looking at the various videos on display and watching levitating debris being melted down into shiny goo, I was about to ditch my job and come look for work for you. It's an exciting field, and I can't wait to see how it all goes. Thank you very much, and I hope that you have a great presentation today.
Thank you very much, Ms. Lively, for your words, and yes, it is certainly exciting. So thank you again, and we hope you can watch the rest of the presentation with us. Back to you, Denver.
All right, so let's start from the beginning. How is that we going to collect this resource, this space debris? So for this, we're going to have Carolyn Belle from Astroscale, a company that has been focusing on how to collect this important resource in space. So Carolyn, here you go.
Thank you. Thank you so much, and delighted to be here with you today and with those of you who are watching us. And it's not just how we're going to collect space debris, but also why we want to. What are the reasons for doing this? I love what the US Consul General just said about enabling the sustainable space exploration and how the generations alive today have an opportunity to make an impact on the world. And that's part of what we're trying to do at Astroscale, is help address this space debris problem. So what is space debris? There are a few different types of space debris, elements that can contribute to this. The first one that we tend to think of are satellites that are no longer in service, defunct satellites. There are also the rocket bodies that put those satellites into their operational orbits, but then fail to deorbit themselves. We also have objects that are released during the normal course of operations. Maybe this is something that is released accidentally during a spacewalk by an astronaut, or maybe this is a latch that is holding a deployable in place before it unfurls. There are also collisions that can cause debris when you have two objects that collide with each other on orbit, whether they're operational satellites or just pieces of debris. And each of those collisions creates untold numbers of new pieces of debris. And there are also breakups on orbit that might happen unintentionally, such as energy that's stored in a battery after a satellite is taken out of service. And all of this space debris, as we saw at the beginning, has built up over the last 60 years in space. And this is something that impacts us because today's society, today's economy really depends on what we can achieve with space. Services like communications to remote parts of the world, whether those are mountainous regions like we have here in Colorado, whether those are islands, such as you see in the Pacific near our partners who are in Australia. There's data that comes from space about the status of the Earth's environment, tracking natural resources, tracking fisheries, wildlife, agricultural yields, mining, that comes from space. Banking and financial transactions. Every time you use an ATM or your credit card, what's happening in the stock market, that all relies on timing signals that are very accurate, delivered from space. Navigation, anything that is a location-based service in your cell phone. Again, all of this is relying on what we've achieved in space, what we have put into space. And that's very beneficial for us today and will continue to be beneficial into the future as long as we can continue to deploy satellites. So what's the problem and how does that link to space debris? Well, orbits are becoming more congested. So here we have low Earth orbit, LEO on the left, and then GEO on the right. So these are two very popular places to put the types of satellites that deliver the services I was just talking about. LEO, up until about 2,000 kilometers, is where we have those that are observing the Earth. Most of the images come from LEO that we tend to see. We also have communication satellites in LEO. And then GEO, here on the right, the furthest ring that you see out, this is about 36,000 kilometers above the Earth. This is where there are the communication satellites. Think the TV, satellite TV, or the satellite radio. Those are active in GEO. But if we think about all of those dots that we see here, that we saw in the initial animation, only about 5,000 of those are operational satellites. The rest of them, say 30,000 objects that are larger than 10 centimeters, which is as small as what we can detect from most of the sensors that we have trained on the sky, most of those are debris. And if we look at the mathematical models that have been built around what is the potential for smaller debris to be in orbit, that hits up towards 130 million pieces of debris. Now that is a lot of material that we have put into space and left there. A lot of material that could potentially be used for other purposes, and while it isn't, it's presenting a collision risk, a threat to those operational spacecraft and to all of our activities that rely on space. And just for fun, we'll see that the problem is getting a little bit more intense because those 5,000 today could be 30,000 by the end of the decade as more services are deployed and more satellites alongside them. And this is an issue that more and more people are aware of. So it's not just those of us in this room, it's not just Astroscale, it's not just academia that are caring about this issue. It's space agencies all over the world. We're collaborating with JAXA, the Japanese space agency, with the European Space Agency, the United Kingdom Space Agency is active in this. And then of course here in the US, NASA is talking about space debris and has been an essential player in defining what is really the risk around debris. And recently, over the last year, then there's been more talk from the Space Force around commercial solutions to address this problem. People like Major General Burt, who you see here, who has said, please give me a commercial trash truck for space because I want to clean up Earth's orbit. And I want it to come from the innovative small companies out there who are able to develop creative solutions to this immense problem that the whole world faces. So there's the challenge. So why is it that I'm up here talking to you? Well, I work for a company called Astroscale US, and we have a vision for space sustainability. So for us, we look at the current way of doing business in space. And that is where you design a satellite, figure out what you want to use it for and how it's going to work. You build it, you launch it, you operate it for say 10 years in low Earth orbit, 15 years in geo, and then you're done, you throw it away and you start over. But we envision a world where you don't throw it away, where if something goes wrong with that satellite, maybe you inspect it and try and figure out what the problem is. Maybe you send another satellite to repair it, to augment it so that it can complete a different mission than what it was designed for. Because the market's changing all of the time. And so satellites and their abilities need to change as well. It could be that you deploy a new antenna to enable it to work in a different way. You extend its life by potentially refueling it. So as soon as it runs out of gas, it doesn't need to be taken out of service. And as soon as it does need to be taken out of service, you remove it from the space environment so that it doesn't create a threatening piece of debris for the other operational satellites that will come after. So this is the service and culture we envision. We are a global company because space debris and the space environment are a common global problem. So our US headquarters are here in Denver. I am a proud native Coloradan. I remember coming up to mines when I was in high school. Our academic award ceremonies were here, so I feel very comfortable on campus. But we also have offices around the world. We have a partner office in DC, working with lawmakers on the Hill, working with NASA, working with other agencies to implement the policies we need to enable sustainability. And we also have sister companies in the United Kingdom, in Israel, in Singapore, and in Tokyo, where our company was founded, that are also working on this challenge. We have about 200 people in the company. We've received numerous awards for some of the creative ideas that our team members have been coming up with. And because of that, we've been able to earn about just under 200 million in investment to put towards the solutions that we'll talk about today. There are three different ways that we are pursuing to address the space sustainability challenge. Now, we often think about space as being high tech, and certainly we're going to see some very cool technology today, and I'm really excited about that. But technology isn't the only way to solve this problem. Technology needs to be developed in tandem with policy and with economics. The solutions that we're coming up with need to be cost effective. We need to make sure that companies, that space agencies, that all satellite operators want to be sustainable because it helps their bottom line, not because the government is telling them that they have to get a license. And so we really need to be taking a multi-pronged approach, and we are very happy to collaborate on all of these efforts with others in the industry, because this is a joint project to be able to get to the places where we need to be for this to be successful. So what are the 4 mission lines that Astroscale is working on today? So we are working on end-of-life services. So this is the mitigation aspect of debris, making sure that we're not creating new debris as we continue to launch satellites, because we want to continue launching satellites. Active debris removal. This is the remediation side of removing those threatening pieces of debris that are currently on orbit. In situ space situational awareness, being able to launch a satellite that can inspect, characterize, understand the space environment from within the space environment. And finally, life extension, which helps to cut that process of operate for 15 years and replace by allowing operators to get additional life, which means additional revenue, additional services out of something they've already paid for. And so we are advancing missions on all of these fronts today, and I wanted to show you a little bit about what our team has been doing. There's normally very inspiring music playing during this, so just imagine epic, like orchestral scores playing in the background here. So this is our ELSA-D mission. This is on orbit today. It launched in March. Oh, there we go. More techno than orchestral. This has been a pretty big vision that I've shared with you. So how do we get there? How do we reach the potential that we see in space? We want to put a dollar amount to it. There have been forecasts that we're going to hit $1 trillion by 2040. Some of them are at $4 trillion by 2040. But to do any of that, we need to be changing the way we work in space. And that is not something that we are going to do alone. Sustainability is not something that any one company can do. It's something we all need to do together. So we are working with other on-orbit servicing providers. We're delighted to be here today because it is a group effort. Each of us have a unique area of expertise, a unique set of technical skills and visions and ideas that we bring to the table. And by combining those, we can achieve much more. So I'm excited to hear about what my co-speakers have to share today. So I will go ahead and pass it off to them. Thank you so much.
Thank you so much, Carolyn, for that presentation. We got the goods. We have collected them. Astroscale is bringing us to us. We have the option to send it down to Earth and let it burn in the atmosphere, or we have the option to probably use it for something that could be more of use to us. So for the second link on the value chain, we have David Marsh that is going to be talking to us about what to do with it, how to prepare it, how to cut it so that then later on could be processed and we can extract some of the goods from it.
Thank you all for being here. Thank you to the Colorado School of Mines for hosting this event. Thank you to the other companies for participating and organizing this. And thank you to all of our guests here physically and overseas and around the world virtually. I just want to echo, before I jump in, wanted to echo the Consul General's thoughts and Carolyn's thoughts as well about how this is truly an international problem. And I think it's remarkable that we have 4 companies here today from multiple countries whose technologies all seem to align so well to solve this challenge together. I think it's a bright future for the space economy and for the orbital ecosystem specifically. My name is David Marsh. I'm the strategic lead for space systems at Nanoracks. And today I'm going to talk a little bit about how we are approaching the orbital debris problem. Specifically, we've been looking at the upper stages. So when a rocket goes up and they leave their disposed rocket body in orbit, how do we prevent that from becoming a problem in the future? We just saw a pretty awesome video of the deorbit technology that Astroscale is working on. And we're approaching the problem a little bit differently, but trying to do it at the same time to support all of these other companies, support the ecosystem itself, and see if we can't create a better future. Nanoracks has been around for 12 years, and over that time, we've deployed over 1,000 payloads to orbit from over 30 countries. Those payloads have ranged from CubeSats built by high school students to the Bishop airlock, which is the first fully commercial module of the International Space Station. Actually, just last week, we demonstrated a robotic technology from a Japanese robotics company called Vitai inside our airlock. This range of experiences has given Nanoracks a pretty significant wealth of data to pull from and to study the trends of the industry. And one of the things that we've started to see is a growing demand for central commercial orbital destinations, where you can conduct business, goods can be exchanged, services can be rendered. We've figured out a way that we can repurpose the upper stage of a launch vehicle to turn it into one of these commercial stations. We call these continued repurposed upper stages outposts. And we think there are a number of significant advantages for using the upper stage. If you think about it, it's a structure that's already built for you. There are already tanks, there's already tons of metal that you can use, and you're solving a challenge. If you remember earlier on from that video that Angel showed, 30,000 pieces of debris, about 600 of those are rocket bodies, but they represent a significant portion of the mass in space. If we can prevent any other rocket bodies from becoming debris, that's an advantage for everyone. If you think about how many launches happen per year, if there's a way to gain additional utility out of each one of those vehicles, it becomes very promising for the entire orbital economy. So in order to take a launch vehicle upper stage that has fulfilled its primary mission and to turn it into a space station, there's some pretty complicated technical challenges that you need to solve. There are primarily 2 of them. First, you need to control the stage. And secondly, you need to be able to modify the structure. So rockets are generally built to only operate in space for a number of hours. Their job is to go up and put their primary payload into an orbit, and then they're done. They normally maneuver themselves into a disposal orbit if they're far away from Earth, or they deorbit themselves. What we've developed is a system that we call the Mission Extension Kit. It does pretty much what the name implies, and it allows us to extend the mission of an upper stage. It provides its own power. It allows us to point the stage. It allows us to provide communications and data handling to any attached payloads, and basically keep it up there as a space station. We're going to be launching our first Mission Extension Kit, or MEK, in 2024. The second challenge, however, actually modifying the structure of a stage in orbit, is a little bit more complicated, but I'll talk a little bit about how we're starting to solve that one as well. So the first step is to show that you can cut metal. And we're doing that with this experiment we call Outpost Mars Demo 1. Mars Demo stands for Multiple Accommodation Research System. And from that, you can tell that we're going to do multiple of these. We're not just going to do it once. We're going to prove that we can cut, and then we're going to iteratively create additional technologies so that show that we can join metal, show that we can manipulate and move around pieces of metal. So we intend for this to be a series of experiments. The first one, however, Mars Demo 1, will be launching in January on Transporter 3, the SpaceX rideshare mission. And we're going to demonstrate what's called friction milling. So basically, a drill head is going to spin very fast, generate a lot of heat, and push through metal. Kind of if you imagine a ship pushing through water as it kind of pushes the surf away, that's what we're going to do with metal. By using this technique, we're hoping to show that we can cut in space in microgravity without creating additional debris. That's the whole reason why we're up here, right? We don't want to actually contribute to the problem. So the entire experiment is going to take place in this box you see there on the right. That's a system we've built called the Payload Service Module. And essentially, it provides all the stuff you need to deal with, the batteries, the data handling, the radios, to allow you to just do the experiment. And so that whole structure is going to be attached to the SpaceX rocket. The mission's going to go up, everything's going to deploy. We're going to show that we can cut metal, and then the whole stage will deorbit, making sure nothing gets left up there. Now I'm going to show a quick little video of a ground test we did of the friction milling system. And I apologize for that black box. Our engineers insisted that I censor that. So if you just ignore that and focus instead on the drill itself. So you can see there the friction milling head starting to spin up. And it's playing. There it is. You should see it start to heat up. And now it's going to start to move through the metal, heating up the contact point, pushing it aside, and the metal will re-solidify back on the sides as it pushes through. This is sped up a little bit, but essentially the system's going to cut at about 10 centimeters per minute for this initial test. And the metal it's cutting through is intended to be representative of an upper stage. So it's the same material that most stages are made out of. It's a thin layer of kind of the skin that goes around the outside of an upper stage. And you can see there it's finished. For our actual test, we're going to be cutting through 3 pieces of metal, varying the speed and temperature control just to get additional data. And this is a picture of a cut after it's been made. You can see there on the right that it looks almost like a normal weld. The metal has been kind of pushed aside and re-solidified. So we're hoping to replicate this in orbit and show that we're not going to create any additional debris. Here I have a picture for you of the system itself. So you can see this is the entire payload service module, but we've taken the lid off. We want to show you inside. You can see in the lower right-hand side the 3 metal coupons that we'll be cutting through. You can also see that robotic arm as well as the friction milling attachment there on the very end. This arm is only 1 degree of freedom. It's just going to cut through the 3. But in the future, we want to take this system and put it onto a robotic arm, allow us to actually cut around the outside of an upper stage, cut the skin off, and then use that kind of shell for other purposes in the future, some of which you'll see here in a couple minutes. But we hope to, after this OMD-1 mission in January, repeat the mission using our payload service module, but for a joining technique. So it's important that we prove these technologies because we have a vision at Nanoracks for using these outposts as space stations to conduct other activities. So if you imagine a scenario where an outpost launches, a mech launches on a rocket, it has a number of other capabilities, such as OMD-1 cutting capabilities, such as a robotic arm, maybe even refueling capabilities, and maybe even you dock a couple active debris removal vehicles on it as well. The whole system goes up, places itself into an optimal location, maybe where there's a cluster of particularly dangerous debris. Those vehicles then can deploy from the outpost, go conduct their activity, but now they have the option of either deorbiting the debris or bringing it back. And that flexibility we think is important for creating an economy around orbital debris. If you could imagine a scenario where, say, a particular piece of debris becomes dangerous, whether there's a collision and a piece flies off and is now on a trajectory where it's going to impact the ISS. If there's a high demand to go get that item immediately, You don't want to waste time to go bring it back. You just want to go get it and get it out of the way. But this solution allows that active debris removal vehicle to come back and refuel and then conduct another activity in the future. If you take that scenario and assume that the debris is coming back to the outpost, then it becomes really interesting. Then you can take that, you can take the LMD1 cutting capability and actually take that material and use it for something else. And so I'll let our other partners here talk about that a little bit more. I am very excited to see some metal get melted. But thank you all for taking the time to listen. Look forward to answering your questions during the panel.
So Carolyn from Astroscale captured the space debris for us. David has just shown us that instead of sending it down to Earth, now we can put it in a place, in a module, and not only that, cut it and get it ready for the third link on the value chain. And so for this, we're going to have Gary Calnan, CEO of CisLunar Industries, that is going to show us what is that we can do now to extract important elements from this space debris. With him is also going to be Joe Pawelski, the mastermind behind this gadget over here, that is going to show us some of the early work that has been going on in terms of proving the technology of extracting the metals and doing things with it. So Gary.
Thank you, Anna. Yeah, this is really exciting. We're very excited to show everyone today the technology we've been developing that can actually make this debris we're collecting, turn it into propellant and other things for orbit. Before we did that, I want to just thank everybody for joining us today. We've got at least 150 people, either in person or online, that have decided to spend some time to join us today and check this out. And so we're really all grateful that you guys could join us. I'm also very grateful to have Astroscale and Nanoracks and Neumann Space as such wonderful, strong partners for us to help us make this thing a reality. We couldn't do what we want to do without many companies participating in this. So it takes all of us to make an economy in space. And I'm grateful to have their support. And of course, most of all, I'm very grateful to have my support to host this event today. And I mean, they've been with us since the beginning of our idea, always been in our corner, and I'm very grateful for that as well. So thank you all for coming. Before we jump into it, I just want to take a step back a little bit, some context around it. So for the last 200 years or so, humanity has become really masterful at manipulating different kinds of matter, different kinds of materials, plastics, metals, ceramics, even 3D printing biological material. So it's really becoming an amazing thing. And this has enabled an industrial economy that has provided a lot of amazing technology that we use every day that benefits our lives all the time. One of the key elements of that technology, of that industrial technology, is economy is metal. Metal is a key piece of that puzzle. If you look at any device you have, you're going to find metal in it somewhere, for the most part. And so we see this industrial economy that's here on Earth supporting us actually going and starting to emerge in space. In fact, it's our belief that there is an industrial revolution happening in space. It's starting right now. And you can see some of the companies that are here today are the ones that are building that foundation to make that happen. And we think that this industrial economy that's emerging in Earth orbit and CisLunar space, which includes the moon, on the surface of the moon, is going to be what allows humanity to actually expand beyond Earth and become a multiplanetary species out in the solar system. And I think it's going to lead to an increase of abundance, an increase in technology that's going to benefit all of humanity, either on Earth or in space. And so we want to be a piece of that. We want to be a part of that puzzle. And our piece of the puzzle is to figure out how to master processing metal in space. And our first device that we're using to get into that is the microspace foundry. So our microspace foundry, what you see here is the prototype microspace foundry. When we get to orbit with this thing, it's designed to be a small scale, distributed metal processing capability. It's a low cost and can be added to wherever we need to process metals in space. We can add the amount that we need to process, where we need to process. What that's going to lead to, and this is cool because what we saw with Nanoracks, and they showed that on the last slide that he showed, which is, I would say much prettier than this one, but this gives you a nice idea of how it fits together, right? We have Astroscale telling us how they're going to go out and get space debris, right, and pick it up. And we've got on this diagram, you kind of see how it all fits together. So if you imagine Astroscale sending out one of these little spacecraft going out to grab that debris, bringing it back to a platform that could be a Nanoracks outpost platform. And they could host some of our processing devices on their platform. We could put as many of them on there as we need to match the throughput of production that the market demands at that point. And there we could process that debris. We could salvage things that we don't need to melt down, but if we do need to melt them down or turn them into other materials, we can process them with our machines and create rods, metal rods. That's the first product we're going to make with this. It could take other forms, but right now, making metal rods, because a metal rod can be used as propellant in the Neumann thruster, which you're going to see in a minute here, which is really cool. So we can make metal rods with that, and we can also use it as feedstock for ingots for other manufacturing processes. And this is how the whole thing kind of begins. We use the processing of space debris as a bridge to be able to build the metal processing capability for that full industrial economy that we know is going to emerge probably sooner than you think. So in the last 6 months, we have gone from a concept with help from funding from NASA, with a NASA SBIR phase 1. It's a little bit of outside investment. We've been able to take it from the garage that you see on the left there, and I can thank Joe for volunteering his garage to be our lab. Joe had a really cool maker's garage there, lots of amazing machinery. He still has machinery, but just not in the garage. We turned it into a lab. We did a lot of our initial testing there where we were melting metal and levitating it. We took that same device to the Colorado School of Mines, and in their Space Resources Lab, we were able to test it in vacuum. And then today, we've upgraded that device to the machine you see here in front of me. So we're about to turn it over to Joe so that we can switch to his screen. But before we do that, I just want to lay out the experiment for you, or what the demonstration is going to be. You've got a couple of molds up here. They're labeled A, B, and C in this configuration, but you can see them here in front of you, or I don't know if people in the remote will be able to see this soon. But, and then we're going to be melting and making one rod. We've added a little bit of extra mass in the mold to accelerate the process, just so we can do it quickly. And then we're going to show you how we can eject another rod that's already been made from a different mold. And so you'll see that how the whole process works. I think now we should click over to Joe's screen. So if you can share your screen, Joe. Great. All right, so what you're seeing in this view here, I'm just going to explain the 4 windows real quick. We've got on the upper left a thermal view, and it's already starting to heat a little bit because Joe started to do the process. On the upper right, we've got a top-down view where we're looking down into the molds. And on the bottom right, you've got sort of a side view that gives you kind of another perspective on how the machine is working. On the bottom left, you've got the control software that we've custom made to run this custom built machine. And so right now, Joe started heating the process. You can smell a little bit like the metal melting, so that's normal. That's what we expect to see, to notice.
We're actually making a rod right now.
We're actually making a rod right now. Yep. And you can see if you look at the thermal view, you see that like blob kind of bubbling there. And eventually, pretty soon, you'll be able to see, looking in the top-down view, you kind of start to see it. There's a couple little blobs there that are moving around a little bit. It corresponds to what you're seeing in the thermal view on the upper left. We can basically put into this system how much of a rod we want to make, and it automatically knows how much ribbon to take. And this ribbon is aluminum 6061, a very standard sort of aerospace grade aluminum that's used a lot all the time. There's a lot of aluminum in space debris. So we decided to start with aluminum as an easy thing it's a little easier to work with than say steel or titanium. And it's a good place to start to demonstrate the process. And so we're using aluminum 6061 as a ribbon because we can use the cutting technology that Nanoracks is developing to cut strips off of an upper stage, of how we're envisioning this might work. And those strips could be fed into here. Okay, some cool stuff is happening now. So if you're looking at the screen, even the side view, you start to see the molten metal showing up there. And if you're in the audience, and you can actually, I don't know if you can see this far up, but you can sort of see a little bit of shimmer at the top there. The other thing that's happening while this is operating is, the mold fills up as it's melting. We're lowering the stage down to keep the melted part, the top of the rod that we're making, always within that coil. The coil that you see around that mold is what's actually heating up the metal. It doesn't heat the mold. The mold is made out of a ceramic that doesn't heat up. So it just heats up the metal that's inside the mold. So you can kind of hear it humming right now. If you're in the room, you can kind of hear it. And what it's doing is it's resonating at different frequencies, and we can cause them. You see the metal, especially in the thermal screen, how it kind of flutters around. It's actually vibrating the metal itself, and we think that this is kind of a hypothesis to test. It's just an area of further study. We think it helps to mix the molten metal while it's fluttering around like that. You can see in the top-down view, you can really see well that it's nice and flat. And by fluttering it around like that, that helps it to sort of level out and become flat. So now we're going to lower the stage down. We're going to rotate to the position where there's already a rod in here. So Joe's rotating mold around. Okay, there's a rod with a hole in it on the top left of the upper right window. That's the rod we're going to eject from the system. Now use these robotic tongs here to pull out the rod. See, in space, we would have the benefit of gravity, just knock it off there. So something will come in and grab it and put it into a storage container or something. And this one's kind of cool because, you know, the rod we're making here, we've simplified it. We're just filling up the mold. But when we make a Neumann rod, we'll have to drill a borehole down the center. That's how their system works. So for people online, you can see the hole in the center. So that's, you know, we'll eventually cast them with the hole already in there. I think from there, let's hand it back down under so that we can see one we sent down to them a couple of weeks ago being used as propellant in their thruster system. Thanks.
Excellent. So what I'm going to do, I'm going to share my screen just to give you a very quick promise introduction of Neumann Space. It's all organized. So Neumann Space is based in Adelaide in South Australia. So we have a much more team than Astroscale. So we have about 9-10 people here. And our objective is to develop and manufacture electric propulsion system for spacecraft. So starting with satellites in LEO and of course, getting bigger. So it's a patented technology that is coming from the research from Dr. Paddy Neumann a few years ago at the University of Sydney. And since then, we went from that R&D phase to engineering. So we actually have engineered models here on the table for people to see. The technology in itself, it's a little bit similar to an arc welder, right? So what it is, it's arc spot being generated from a center trigger on the rod that you have seen. That's why Gary was talking about that hole in the middle. So the spots are generated at the top of the surface in the middle, and then they go along the cathode surface. And as they do, they erode the metal into space. And that ejection into space with the principle of action-reaction is where you generate thrust. So the propulsion system that we have is really made of two components. The PPU, as Gary also was talking about, so all the power processing unit. I'm not going to talk about it. And the thruster unit. The thruster unit is an anode cathode system. So that's what you see on the left, the right part of the screen, sorry. And the dark gray is where the CisLunar rod will be. All right, so I mentioned that because when you see the video, the live demo, this is what you're going to see. It's that right-hand part of the system. I'm not going to talk about any performance here, but the idea is really that we're using solid metallic propellants. And that's important because it's completely inert, it's non-toxic, you can store it, it's easy to ship to a worldwide regulatory environment, it's much easier. It provides a lot of benefits compared to other propellants. And the system we have is scalable. So the system you see here and that we have on the table here is an old one, where it was one designed to do some initial testing for CubeSat. So only very limited amount of power in this one, but when we have a platform with the type of power that Gary was talking about, then we can do a lot more powerful system. Where we are in our technology development and future demonstration, we are part of a project in Australia called Spirit that is funded by the federal government and the Australian Space Agency here to fly a 6U CubeSat at the end of next year that will onboard the propulsion system from Neumann Space. So that one is critical for us because it helped us in a matter of a bit more than a year go from a Tier 5 level to an EQM model that is sitting on the table with us right now, and that will fly next year. Now, all this is about using propellant that we can source in space to recycle metal with the partners that we have seen before. It's all important because of the cost of propellants in different systems today. And the interest with the post-cathodic arc thrusters, so the type of technology we are using with metallic propellants, is that they are reasonably cheap compared to others. They can be stored for a long period of time. They are not subject to radiation. They don't need tanks, pipes, a number of things like that. So they are really good. And you can see that vision that Gary was talking about with, grabbing, satellites or debris in space and having a junk hunter kind of spacecraft going around eventually and removing all this. So this entire chain and value chain from getting a debris, removing it there so that other satellites can take the place, limiting the risk in LEO and in space in general. There are a lot of values everywhere, and also, of course, to using that fuel or that metal as propellant. So this is very quick introduction of what we do. Now, what I'm going to do before we do the live demo, I'm going to run a quick 2-minute video that is really specific to the way we worked with the rods that were provided by CisLunar. Because when they called us, they said, look, can you take that and show that you can generate thrust with it? All right, so we did that, and I'm going to show you how we did that.
At Neumann Space, our team of engineers designs, builds, and tests the complete propulsion system comprising the thruster unit, power processing unit, and software. We have tested our patented technology using solid metallic propellant rods such as magnesium, vanadium, and molybdenum, all cast on Earth, until we received out of this world CisLunar Industries aluminium 6061 rods cast in vacuum. Using these propellant rods in our thruster, we forged the first link of the in-space recycling value chain. To prove thrust, we fitted a CisLunar rod in Neumann Space first practical demonstration hardware. We used a torsional pendulum thrust balance developed in collaboration with the Australian Department of Defence DST group. After pumping down to reach LEO pressures, we initiate the firing sequence. Firing. The damped oscillation showing on the display monitor is proof of thrust generated from the CisLunar propellant, as is the flash of plasma visible through the steel vacuum chamber viewport. To better showcase plasma generation, we used a molybdenum rod in an acrylic vacuum chamber. And for clarity, paused on the one frame capturing the plasma plume. New propellant sources shall soon be available on orbit for the Neumann Space thruster. G'day, I'm Paddy Neumann. Welcome down to the lab. In front of you, if you're joining us via Zoom, you can see a close-up view of some early development hardware we've got. Centered in there is a 25mm aluminium cathode from our good friends and partners at CisLunar. It is in an acrylic vacuum chamber. For everyone else in the room, the plasma discharge will be bright, but the acrylic is opaque to ultraviolet, transparent in the optical and radio bands. I've got it set up to do 50 pulses once every 5 seconds and about ready to go. Now, every 5 seconds or so, there'll be a very bright blue-white flash of light coming out of the front end of there. You'll see some reflections coming around from the interior surfaces. And just looking at the camera we've got, we're capturing quite a lot of that, and also capturing some of the light from the trigger event as well. So what we've seen today is potential ways of reaching the resources, moving it around to the refinement site, the factory, how to process the material so it can be remade, the actual remaking, as well as a recording of how you actually use this to generate thrust in space.
Herve, thank you so much for showing us the last link on the value chain. Now we have seen what the possibilities are on dealing with space debris. So now it is your turn to ask questions to all these different companies of anything that you have seen so far.
I just want to add another element of gratitude. Come over here. This guy has been so instrumental for us today, especially, but has been with us from the very beginning of all of our mine supporters, which are tremendous. Angel has been the strongest, and I mean, you know, he probably felt a little nervous from time to time as this thing was coming together over the last few weeks, but he hung in there, and I'm super grateful for all you've done for us, Angel. So we made this special little token of our appreciation. This is the rod that we use for to show that was coming out of the ejecting from the mold. We made a little stand for you. Jeez, to keep as a souvenir from this first demonstration of.
Precious as any space that can come from Earth. This is the first. What you're doing, you're seeing here the very first integrated demonstration of what to do space. This is a historical moment. So now, thank you so much for that. I really appreciate it. We're so happy to be supporting all of you in this step. So now let's go to the questions. Now thank you for letting me come today. Thank you so much. Now we have something from Zoom and Carolyn. Can you talk about unprepared debris removal, or is it the near-term market opportunity dependent on satellite manufacturers, including interfaces, specifically for in-space service?
Yeah, it's a really good question. So we're planning to do both prepared and unprepared capture of debris or operational spacecraft. The unprepared is really important because everything that has been put up there, with the exception of some of the OneWeb satellites recently, was not prepared. It was not designed with servicing in mind. It was not designed with either a place to grab onto it or what we call a fiducial pattern to be able to safely approach and know exactly what you're looking at. So we are working on capabilities to do that. That would be important for not necessarily everything that might be used by CisLunar, because we hope that in the future, pretty much everything is launched prepared so that it can be serviced. But hopefully what's already up there can be used by you guys in the future. If it has the right composition, if what it's made of is something that they can turn into something that a customer wants, whether that's Neumann or someone else, certainly they're the first of many customers you'll have. We want to be able to do that. So being able to capture unprepared debris is important. So how we do that is a safe rendezvous process. That is step one, being able to safely approach that client, as we call it. And then being able to identify what is a structurally sound location on that client at which we can grapple it. And then we've developed multiple different ways to do it. So what we showed in the video was the magnetic, that's for prepared. We also have a robotic team that is working on robotic arms that would be able to capture that unprepared object as well and then safely maneuver it to wherever it needs to go. So, yes.
Thank you so much. Very good. Let's move now to the second link of the value chain. Any questions for Nanoracks, David Marsh from?
Yes. I just have a question before that, which is what additional value might come out of it? What additional value might come out of the technology of being able to catch debris? That's sophisticated maneuvering spacecraft. Right. So what else might we see from that? Or just capture debris.
Angel, can you restate the question for us because we cannot hear the questions here? Thank you.
Yeah, so the question was looking at the technology that needs to be developed to be able to capture and maneuver debris. Can we deploy that technology in other areas to deliver other types of value? Yes, and that's something that we're looking at doing. So it's not just debris, it's also if an operational spacecraft wants to be moved from one location to another. Say it doesn't want to use its own propellant, doesn't have enough propellant to do the inclination or the altitude change, we could do that service for that client. The life extension that we're looking to offer also leverages this same type of capability. And really you get from there into the broad sorts of logistics that might be involved in a more dynamic commercialized space ecosystem. So this is something, I'm sure Dave can talk about what other visions Nanoracks has and you know, the parent Voyager has for what the space industry could become. But we envision regular logistics happening between different orbits, right? As we're not just LEO, MEO, GEO, but we're also CisLunar, right? We have the limitation to just around the Earth anymore. So there are going to be more activities happening in space, and that means things that need to be moved from point A to point B. We want to be able to do that for them.
Good. Yes, one more from here.
Another question for Carolyn. You discussed how Astroscale is focused on technology, economics, and policy. I was curious to dive into some of the policies that you're trying to lobby for.
Yeah, absolutely. And it's not, repeating the question is, I had mentioned that we focus on technology, policy, and economics. So could I dive into some of the policies that we're looking to push forward at the federal level? I would say, first of all, it is not just at the federal level. We are looking to change policy and support the formulation of smart policy around the world, because this is something that, yes, needs to be done at a national level, but we also need international collaboration. We're excited to see that. But here in the US, what are we doing? One of the most obvious things I think to talk about that most of us will have heard about is this general guideline for 25-year deorbit. That as soon as a satellite in LEO reaches end of life, you have about 25 years to remove it from the LEO environment. It's not a hard and fast rule, so many people don't abide by it, but even so, we think it's too long. We think that something on the order of 5 years is more appropriate for keeping the space environment sustainable in the context of all of the new satellites that will be launched in the coming years. Right, so that's one area. Another is when the FCC looks at licensing constellations, how is it that they look at the risk around those constellations? And so they look at something called probability of collision. And for a long time, that was looked in the individual satellite level. So what is the probability of collision of one satellite in this system with anything else? We are encouraging them to look at PC aggregate. So if you have a satellite constellation that is 30,000 satellites, what is the overall probability of collision of all of them together? Because we're not just looking at one satellite in isolation. So those are two examples of areas that we're looking to inform policy. But overall, it is about looking at the norms of behavior that satellite operators need to engage in and abide by in this new economy in space that all of us are looking to do as things become more complex, as you have servicers moving back and forth, as you have upper stages being used for alternate purposes after their launch, as you have foundries in space, as you have manufacturing using these products for other applications. It's going to be a much more complex environment, and we need to make sure that all those space actors are behaving in ways that others can anticipate, in transparent ways that are safe, so that we can move further.
Very good, thank you so much. Actually, in another non-technical question, now this is for David Marsh. What are the regulatory challenges in the US for transferring ownership of an upper stage and turning it into a satellite that stays in orbit? Have you done any research planning, future space policy? Who owns the space?
Yes, absolutely. So that's a fantastic question. Carolyn already touched upon some of the aspects there. In short, it's a very complicated regulatory challenge. It's an international problem. It's a U.S. government federal problem. It extends beyond that. It involves multiple actors within the U.S. government. The way that we're approaching it from our planning purposes, there's basically an easy way you can do it and a hard way you can do it. We're doing the easy way first, which is we're launching on a vehicle with our mission extension kit attached to that vehicle, where we have a relationship with a launch vehicle provider, and then we're adapting that upper stage first. So that allows us to have a pre-characterized relationship. Everybody knows exactly what's happening, and we can have a formalized handover process between the operator of the stage and Nanoracks once we become the operator of the outpost. If we're approaching other debris, whether it's to attach our system onto that debris or to recycle it into something else, that becomes a much more complicated regulatory challenge. And that's one that we're not trying to solve today. We're starting the process. It's going to be a long-term challenge. But we're hoping that by doing the easy way first and showing that it's possible to repurpose an upper stage, we can prove the ground and make it easier for us to do more complicated operation in the future.
Thank you so much. And this only shows you how multidisciplinary is the field of space resources. Just in the audience, we have scientists and engineers, but we also have policy analysts and even lawyers, which are going to be involved in this process. So thank you so much, Dave. Now we're going to go to the very heavy-duty technical questions for CisLunar. Let's get started with how does the molten metal move down the mold without gravity?
Right, so in the way we've configured this device, the idea is that we would use the electromagnetic fields that are generated in the melt that we're forming in the mold. The coil is configured in such a way that it's above where that melt is. So we'll use those electromagnetic fields to push down the molten material into the mold. And that's how we'll do it with this kind of more relatively simple setup of having a mold to cast a rod into. We have lots of ideas about how we can use magnetic fields in a variety of ways to control liquid metal on orbit, but the simplest way here is just to position our magnetic coils so they're pushing down on the melt. And that should work in microgravity as well.
And I'll add to that, as part of this demonstration, we didn't show that to you today, but we actually can levitate metal, and we can float it against, the force of gravity. So, if we can move it against the force of gravity, then we can certainly move it in microgravity. So that's technology that we're working on developing right now.
Another one which is interesting, how will materials be triaged? There's radioactive, corrosive, hazardous, coated materials.
Yeah, we're going to try to go after the similar materials first. This is sort of the same kind of answer that Dave just gave. We're not going after radioactive material first. And we're sort of relying on our partners who are going out and getting the debris to be the ones to assess what that debris is, to know what they're going after. We're not going to know for sure how things have changed if you're going after a very old stage that's on orbit, but we should at least have some, in the beginning, I'm sure we'll be going after American upper stages just for political reasons and legal reasons. And, we might be able to talk to people who built the thing in the first place and know what they put into it, have a sense of what it is. So triaging after we get down to more complicated things, we don't envision we would melt down everything into one, agglomeration of material. It would be separated mechanically. There will be copper wires that need to be pulled apart from the aluminum skin. And we think that that's going to be a job for a robot and possibly some human operation or targeting of different pieces. That's kind of
I can add to that. One of the really cool things that we found here is that doing some basic analysis, we can take 1-2% of an upper stage, and that's enough to move it. So we might move these things to a salvage yard or something to begin with, where we can actually dig into them and really get a lot of the other things out of there. But that really simplifies the process. If we're just trying to cut off a little bit, make that propellant, and then move to the next spot, that could be really interesting.
Are there any future plans to test in vacuum or space environment?
we tested the system in vacuum chamber here at Mines actually as part of our NASA Phase 1 SBIR. So we were doing that, and we have plans, that moving into the future plans, we do want to go into parabolic flight to test how this works mechanically in short microgravity. And we do want to take it up to the space station, do a demonstration in extended microgravity in different levels of atmosphere. We'll definitely have plans.
Finally, how are the thermal effects of the process?
That's thermal guy here. So interesting enough, melting metal, especially at the rate that we're doing a few kilograms per hour, is not entirely energy intensive as you might think. Now, certainly smelting aluminum would be. We just are recycling aluminum. So the amount of heat we're working with this furnace here, you can see it's doing about 1,800 watts on orbit. Our goal is to get that down to around 1,000 watts so that we can use some of the infrastructure that's already existing. But it really has to do with the rate that we process at. And for us, the problem is cooling. So in vacuum space, all you have is radiant heat transfer. So we have to think about how much mass we have to carry to radiate that. Now, the really interesting thing about a rod, though, is that we really need to just get the outside solidified. So some of the things that we're looking at is, can we just get these rods, get the outside solidified, and then maybe just let the vacuum of space cool it off over time. It could take a real long time. So there's a number of ways we can look at that. One of the other things that I'll bring up is a lot of times we talk about thermal for spacecraft. It's because part of the spacecraft is facing the sun, it may be very hot, the other side is very cold, and there's a lot of problems with that. Our goal is to be inside someone else's spacecraft and let them solve those problems. So we'll give them the requirements for how much heat we need to get rid of, and then but we'll be inside the spacecraft. So some of those more complicated heat problems we're not worried about right now. You got plenty to worry about.
Any other questions from the audience? Yes.
Back to regulatory piece, are the commercial space satellite operators sitting alongside you at the table in those discussions with lawmakers? Or are you on your own now until you create an environment where you can?
Yeah. Question was, are satellite operators with us or any of us at the table when we're talking to regulators? And the answer is yes. I mean, well, not always, right? Not 100% of the time, but definitely operators are engaged because it is in their best interest to have a regulatory environment that they have provided input to, and that enables all of them to be successful. No one wants to see a world where policymakers just enact policy without having conversations with operators. And so they're very engaged with providing input and even starting to sort of self-regulate at some level to say, we want to be responsible space actors because we want to continue replenishing our constellations, delivering business, making money, because that is what we exist for. So yes, many of them are engaged at the moment and in other areas.
Yes, I was curious, when you're talking to the other people who are building these satellites, do you tell them the parameters that would be good for recycling? Like, yes, if you use these materials, it would be optimal, or do this, because if they know what you're trying to optimize, maybe they could change the way they're building certain things.
Some debate as to who was going to answer that one. So the question was, are we talking with operators about what sort of materials would be desirable to recycle in the future so that they can use that to inform their designs? I don't think we're at that point yet. This is something that the technology is obviously advancing from where it was when you started the company, Gary. But when we're starting to think about design cycles on satellites today, then their lifetime, then what's after, I think it's a little bit early for those operators. It's hard to remember when we think of space being so cool and high tech that we're a very risk-averse industry, and we're very slow to change. And this is something that I think all of us are on board with trying to change. We're all out there with some would say wild ideas, and I think ultimately they'll be implemented. But when it comes to changing the design, and especially on a materials level, that's a bigger question. And then I think another question, which Gary and John might turn to you being a little bit more engaged here, materials that are already on orbit that are very useful and that are very common in spacecraft, right? So materials that would be designed into a spacecraft today probably are going to be designed into a spacecraft 15 years from now, and so that might not even be a question that is so much of a barrier right now to address. One of the things we are pushing for design is preparing spacecraft for servicing, so that it's easier for us to go and grab onto them. Maybe they prepare not in terms of changing the materials, but in how the materials break up, right? I mean, Gary was just talking about having to undo copper wires to get to aluminum. Maybe there's a way that we can design in that process to be more straightforward and more cost
Are there any for Australia? We got those guys still online. Anything for Neumann?
They're on the panel. You can't see them here, but
yes, there's one.
For Neumann Space, can you share any details about performance? So ISP, how does ionization energy for the metals I'm looking at compared to like more conventional ion propellant like xenon or krypton, and how would that affect like power efficiency and stuff like that?
Yeah, this question is for Neumann Space. Can you share anything about the parameters or what do you say?
Like the performance.
Any performance, ISP, all of those things. Can you share a little bit about what is that you can get out of those devices?
So, short answer is not yet. We're just starting doing testing for CisLunar with the rod they sent us. Paddy Neumann did a lot of work previously using different fuels, so not only aluminum like we are talking about here, but others. But then it all depends on the power processing unit that drives this, and there are so many parameters that it's difficult to really give an answer. And then, of course, there are some commercial in-confidence aspect into this. However, like to give you an idea, the thruster unit that we are using for CubeSat today is roughly 2000 ISP at micronewton level. But again, that's using only, 30 to 50 watts. So it's not what we're talking about here. If as I had on my slide, the performance is scalable with the power. So the more power we have available, the better it is. Then, of course, the power depends, or the thrust, sorry, depends on the type of fuel. So I can refer you to Paddy's thesis if you want for some data on that. But again, we have no data to share yet with regard to the CisLunar rods.
I believe there's also part of the question about ionization levels.
I missed that, sorry.
Yeah, the pulsed arcs tend to give much higher ionization states and some multiple ionization states when compared to other electric propulsion systems. I believe I overheard Xenon and Krypton coming through there. They're generally optimized for only having single ionization, like just 1+. In certain refractory arcs, the most common ionization state is actually the 3+ ionization state. So anything that utilizes electromagnetic fields to help accelerate, guide, control the arc gets a lot more benefit per ion because of the higher charge state and often higher charge to mass ratio. I hope that answers that part of the question from the floor. Beautiful, awesome.
Questions from Neumann Space. All right, so we come to the final question. It's a little bit more global question here, so for any panelist. How do you intend to create an equitable, diverse, and culturally sustaining dynamic within this new world as you build the future of space technology and space-based industry as a whole?
Well, interesting enough, Laurel School of Arts and Technology, elementary school, is 2 blocks from our laboratory. And I understand some of the students from there are watching right now, joining us live. So, we're really excited about that. We try to encourage STEM education as much as possible and do these kind of demos for kids that are coming up. I know certainly, just watching rocks as a kid is what inspired me to do this. So I think that's the key part, is we keep getting kids inspired by this sort of thing. Do you guys have any?
So Nanoracks also has spun off a public benefit corporation called Dream Up that helps high school and university students, even middle school students, run competitions, put together experiments. We have these really simple experiments called mix sticks, where basically students can put together chemicals and see how they behave together in microgravity. So we help students run experiments to the International Space Station all the time. And that's something we hope to leverage with our Outpost program as well. There's a way that we can show kids that, they can put one of their experiments onto an upper stage, whether they can be a part of something recycling metal. That's certainly something that we hope to leverage as well.
I think there are a few different elements to that. It gets back to how I started my career in nonprofit work, trying to get kids excited about space and just, going to schools, and all of us who have a background in this sharing the wonder of science, and that science isn't necessarily something you get from a textbook, but it's something that you can see and be curious about and be amazed by and actually do yourself. Where often it's seen as somewhat separate. So I would call all of you and all of you watching to look up that elementary school that's 2 blocks from your lab or from your house, and go see if they want to talk to someone who's involved in space. Going to the more equity, I think, side of this question rather than the diversity and inclusion. is something that is at the heart of space sustainability. Those of us who have been first to space have been able to do essentially what we want in space. And there are many countries around the world that haven't had that opportunity yet. And so making sure that we keep space sustainable so that they don't miss the opportunity to launch their own CubeSats and then microsats and geosats and everything where they can derive the same benefits from space that those of us in the US and other early space actors across the world have been so privileged to be able to do. So that's something that I think will hopefully contribute to as we keep that happening.
Angela, if I can add a word here. At Neumann Space here, we have 4 interns in the room today. One of them actually wrote the code that controlled all the lab environment that was used today, all the interface. And the other ones are involved with different aspects of software development, for example, for first mission. So yeah, STEM education enrollments, you know, education here in Australia with the agency also and others is very key.
So on that note, the bounce from Australia all the way up to Colorado, we want to thank the 4 of you for showing us not just what the space debris value chain is, but what new space is all about. These are risk takers. How can a more non-risk averse can you be than to show your technology in front of the world and to see what happens? That's why I was so afraid. But this is what it takes. It takes bold people that are actually making this new space possible. And we're starting with a human-made resource. Imagine what we can do with resources from the moon, Mars, and beyond. So thank you all for being part, like I mentioned, of this very unique event that shows for the first time what can be done when companies come together with space agencies to look at the entire value chain of space debris. Thank you for coming. And one last thing, one last homework for all of you. When you go back home tonight, look at the beautiful night sky, just like I was saying at the beginning, October 3rd of 1957. Yes, look at the beauty of the sky and all of these shining, twinkling stars. There's going to be Jupiter and Saturn up there and the moon. But also look at all those moving objects from north to south, from east to west, and think what they're doing for us now in our civilization. But think of what can happen at the end of their life, when things like this can be actually be part of those objects that are floating around. And those are the things that are going to enable us future exploration and the future of CisLunar. Thank you all, and Astier.